Good morning to one and all, and welcome to Register class. Myself Narendra A, lecturer from Government Polytechnic Chintamani. In the last session we have discussed what are the concept of the composite sections and what is regarding the thermal stresses and the strain energy. In this class we are going to discuss the problems on composite sections and thermal stresses and strain energy. I already told about the composite sections. Composite sections are nothing but if we use two or more different materials together, we can call it as a composite section. So that your problem is while analyzing the composite sections. Here, which of the section, how much of load is sharing, and how much of stresses are developing, and how much of strain is occurring in the different materials. So that is very difficult to analyze the materials because we have to analyze separately, because load carrying capacity of a one material is different from other material because it regards on the type of a material and composite sections. So that in this section, in this chapter and in this session, we can discuss the problems on composite section, so that how much stress is sharing and how much load is sharing and how much straining occurring in this section. Let us discuss the first problem that are given as a reinforced concrete column 500 mm by 500 mm in section is reinforced with 4 steel bars of 25 mm diameter placed at one at each other corner. The column carries an actual load of 2000 kN. Find the stresses in concrete on steel bars. Take Young's modulus of steel is 2.18 10 to the power of 5 Newton per millimeter square, and Young's modulus of concrete is 0.14 into 10 to the power of 5 Newton per millimeter square. Here concrete column is given of 500 mm by 500 mm size in section and has 4 steel bars placed at each corners, and total column carries 2000 kilonewton load, and here Young's modulus of two different materials given here. So that we can note down the problem here. First of all, before starting of the problem, we can note down, we have to write the section that here we have a concrete column. Here we have a concrete column. Here a concrete column. Steel bars are placed at the corners. Steel bars are placed at the corners. Here steel bars are placed at the corners. Bars of each have 25 mm dia. 4 bars of 25 mm dia. 25 mm diameter, and the column has size 500 mm by 500 mm. Column has size 500 mm by 500 mm. 500 mm by 500 mm. Here concrete column. It is a composite section because it is made up of both concrete and steel. It is made up of both concrete as well as steel. So that its column size has 500 mm by 500 mm. Here the given data as size of the column. Given data size of column 500 by 500 mm. 500 by 500 mm. So another thing, area of steel bars. Area of steel bars. So that is called, you can call it as AS. You can call it as AS. So you are given as a 4 bars. You are given as a 4 number. You are given as a 4 number. So 4 into area of each bar, because it contains 4 bars. So if you calculate area for 1 bar, if you multiply by 4, we will get area of 4 bars. So it is given as a 25 mm dia. It is given as a 25 mm dia. So that area AS, area of steel, is equal to 4 into pi d square by 4. So 4 into pi 3.14 into d is 25 mm. D is 25 mm. So 25 square divided by 4. 25 square divided by 4. This is the area of steel. So that it will get 1963.49 millimeter square. This is area of steel. This is area of steel bars. This is the total area of steel. This is not a single bar, it is the total area of steel bars. So next step, we have to find out what is the area of concrete, because it is a composite section. Now we are calculated what is the area of a steel only. Now we can, before calculating the area of concrete, let us consider what is the area of column. Area of column. Area of column is a given area of column as 500 mm by 500 mm. 500 by 500 by 500 mm. We will get 2,50,000 millimeter. We will get area of column as 500 by 500 mm. We get 2,50,000 millimeter square. This is the area of the column. So our intention is to find out now what is the area of the concrete. Our intention is to find out what is the area of concrete. So see, because we know area of column, and we know what is the area of steel. If you minus the area of steel in the area of column, we will get area of concrete. If you deduct the, now we need to find out what is the area of concrete. If you deduct area of steel in area of column, we will get, what is the area of concrete. Area of concrete is equal to, we have area of column is equal to 2,50,000 minus 2,50,000. We have area of steel is equal to, 1963.49, which I have already calculated. So we will get area of concrete as a, 248036.51 millimeter square. This is the area of concrete. This is the area of concrete in the column. So next step, now we are calculated what is the area of steel and what is the area of concrete and what is the total area of the column. Now our intention is to find out what is the stress. Our main intention is to calculate as to find out what is the stress developing in concrete as well as stress developing in steel. Stress developing in concrete and stress developing in steel. So before coming to that point, in this composite section we know that strain in steel is equal to strain in concrete. We know that in composite section strain in steel is equal to strain in concrete. We know that in composite section strain in steel is equal to strain in concrete, because the ratio of stress versus Young's modulus remains same. The ratio of Young's modulus and stress remains same. So Fs by ES is equal to Fc by EC. This is very important expression. That is, strain in every section remains same. The changes undergoing in every section is same. So the ratio of stress versus Young's modulus and ratio of concrete stress and Young's modulus of concrete remains same. So that's in composite section we have to remember. Suppose if in composite sections contains if another materials, means the strain in that material also will be same. So that by using this, substitute the values of ES and EC in this expression. You have to substitute the values of Fs and Fc in this expression. So we know that Fs by ES is equal to Fc by EC. Here only ES is known, EC is known. Here only Young's modulus of steel is known and Young's modulus of concrete is known. So that Fs is equal to, we have to express Fs in terms of Fc. So Fs is equal to Fc into ES by EC. Fs is equal to Fc into Es by Ec. So Fs is equal to, you write it as Fc, same Fc and substitute the values of Es. Substitute the values of Es. We know that Es is equal to 2.1 into 10 to the power of 5, 2.1 into 10 to the power of 5, and Ec as 0.14 into 10 to the power of 5. You write it as you substitute the values of Es and Ec, 2.1 into 10 to the power of 5 divided by 0.14 into 10 to the power of 5. 10 to the power of 5, 10 to the 5 get cancelled and remains the value as Fs is equal to 15 Fc. You get a expression for Fs in terms of Fc. We will get expression for Fs in terms of Fc. So it's very important here. Now we know that total load is equal to, we know that total load is equal to, load shared by total load is equal to load shared by concrete plus load shared by steel. We know that total load is equal to load shared by concrete as well as load shared by steel. So total load you can call it as a W, so that P load shared by the concrete, so PC plus PS we can call it as total load. W is equal to PS by PC plus PS. We can call it as an equation number 1. So in this case, so this we can call it as a equation number 1. Now we know actually Fs is equal to 15 Fc. We know Fs is equal to 15 Fc. So that we can convert this in terms of load into stresses. We have to, so that from this expression we can convert this load into, this expression in terms of load into, we can convert into express in terms of stresses. We can express in terms of load into in terms of excess, because we know the value of Young's modulus. We know the value of Young's modulus as well as stress value, so that we can express this load in terms of stresses and Young's modulus. We know that Young's modulus is equal to, Young's modulus ES is equal to, first of all we know that Young's modulus is equal to, we can express in terms of load into in terms of stresses. We know stress Fs is equal to PS divided by AS. We know that Fs is equal to, Fs is nothing but stress in steel, so that is the ratio of load divided by area. So we need this PS in terms of Fs. So PS is equal to Fs into AS. Fs into AS. We can call it as a equation number 2. So as usual, so Fc is equal to PC divided by AC. This is the load shared by the concrete as well as the area of concrete. We need what is actually PC. So PC is equal to Fc into AC. This is equation number 3. So in the next step, substitute equation 2 and 3. Substitute equation 2 and 3 in equation 1. substitute equation 2 and 3 in equation number 1. Now total load W is equal to, we have PC is equal to FC into AC, plus Fs into AS. So PS is equal to Fs into AS. Now the substitute the values of, we know the value of W, we know the value of W, that is the total load, that is 2000 kilonewton. We know W is equal to 2000 kilonewton, that is given data. That is the load carried by the column. This is the load carried by the column, so that this can convert it into newtons, that is 2000 into 10 to the power of 3 Newton. W is equal to 2000 kilonewton, so that this converted into Newton, that is 2000 into 10 to the power of 3, that is called Newton. So we have substitute the values of W, FC, AC, Fs and AS in the equation number 4. Substitute the values in equation number 4. Substitute the equation in equation number 4. Substitute the values in equation number 4. So we have total load is equal to, 2000 into 10 to the power of 3, 2 to 3 is equal to, this is the total load W, what is the actual load carried by the column, 2000 into 10 to the power of 3. Now you keep it as FC only. Now we know that the area of concrete is 248036, 248036, 248036.51, and now you have to substitute, now it is the expression as Fs and AS, so that 2000 into 10 to the power of 3 is equal to FC into 248036.51 plus, you can substitute, we developed an expression that Fs is equal to 15 FC, you substitute this, because if you express Fs in terms of FC, it is very easy to solve the equation. If you substitute the value of Fs in terms of FC, it is very easy to solve the equation. So Fc is equal to 248036.51 plus 15 Fc into, substitute the value of what is the area of steel as 1963 1963.49. If you solve this, we will get FC as 2000 into 10 to the power of 3, 2000 into 10 to the power of 3 divided by, we have to solve this and we have to multiply 15 by 19 into 63. Totally we will get FC is equal to 2774.88 2774.88.86. So if you solve this, we will get stress in concrete as 7.2 Newton per millimeter square. We will get stress in concrete FC as 7.2 Newton per millimeter square. This is the actual stress in concrete. This is actual stress in concrete. Now we know the expression. Fs is equal to, Fs is equal to 15 into Fc. If you substitute the value of Fc, we will get, 15 into 7.2. Fs is equal to 15. Fs is equal to 15 into 7.2. We will get Fs as 108 Newton per millimeter square. Fs is equal to 108 Newton per millimeter square. See, this is our answer. This is our intention, is to calculate what is Fc and Fs. So this is the stress developed in concrete as well as stress developed in steel. This is the stress developed in concrete and stress developed in steel. See, first what we have done is, first we have write down the sketch of the given dimension. Here both concrete and steel are given. Here 4 concrete rods placed at the corners in the concrete. So first we have calculated what is the area of steel. First we have calculated what is the area of steel. In the second step we have calculated what is the area of concrete. In the third step we have calculated both the stress, we have developed equation. So after calculating the area of concrete and area of steel, we have developed an equation, the stress in steel in terms of stress in concrete. In the second step, we have developed an expression stress in steel in terms of stress in concrete, and this is substituted in load equation. That is, the total load is equal to load shared by the concrete as well as load shared by the steel. So after substituting the expressions in this total load expression, we will get the stress in concrete. By using Fs, stress in steel in terms of stress in concrete expression, we will get what is Fs. So that this is our intention, is to calculate what is the stress in concrete as well as stress in steel. Okay, we can solve another problem in the same concept, that is composite section. For examination point of view, it's very examination point is very important concept. So the second problem, it's given as a reinforced concrete column 300 mm by 300 mm in section, reinforced with 8 steel bars of 20 mm diameter, placed at one at each corner. The column carries an axial load of 360 kN. What is the stress in the concrete and steel bars? Take ES and EC and also find what is the load shared by each concrete. What is the load shared by in each, both concrete as well as steel. This is also the same type of problem, so we can solve. So it's very easy, it will become very easy in the examination point of view, people. So that here given us area of column as a 300 mm by 300 mm. Area of column as a 300 mm by 300 mm. Here given area of column as 300 mm by 300 mm. Here one thing extra is, here in the last problem we have calculated only the stresses. In this problem we have to calculate what is the load shared by each unit. In this problem we have to calculate what is the load shared by each unit. Here 8 bars are given, that is placed side by side. Here 8 bars are given. Here 8 bars are given of dimension 8 bars of 20 mm dia. 8 bars of 20 mm dia. Here given 8 bars of 20 mm dia. So before starting of the problem, we have to calculate what is the area of the column. First step we have to calculate area of column. In the first step we have to calculate what is the area of the column. So 300 mm by 300 mm. 300 mm by 300 mm by 300 mm, that is, we will get 90,000 millimeter square. 90,000 millimeter square, that is the area of the column. So that now after calculating the area of column, we have to calculate what is the area of steel. Area of steel. We know that here we have, column contains 8 bars. So if we calculate what is the area of 1 bar, we will get, if you multiply by number 8, we will get total area of steel. So 8 into area of 1 bar. 8 into area of 1 bar. So we will get area of steel is equal to 8 into area of 1 bar. So 8 into area of 1 bar is pi d square by 4. Area of 1 bar is pi d square by 4. Here given diameter of the bar is 20 mm. Here given diameter of the bar is 20 mm. So 8 into pi d square, this is 20 mm, pi d square divided by 4, pi d square by 4, we will get area of steel as, 2513.27 millimeter square. This is the area of the steel provided in this column. This is the area of the steel provided in this column. So next step, we have to find out what is the area of concrete. In the second step, we have to calculate what is the area of concrete. We have the total area, and as well as we know the area of steel. If you deduct area of steel in total area, we will get area of concrete. See, here we know the total area, and as well as we know the area of steel. If you deduct area of steel in the total area, we will get area of concrete. It's very simple. So area of concrete AC is equal to total area of the column is A minus AS. We know the total area is 90,000. Minus area of steel is 2513.27. This is the area of steel. We will get area of concrete is, area of concrete is 87486. 87846.73. 87846.73 millimeter square. This is the area of concrete. In the first step, we are calculated what is the total area of the column. In the second step, we are calculated what is the area of steel. In the total area, we are deducted the area of steel. We got area of concrete. So that after calculating the area of concrete, as usual, you know that in composite section, strain in every material remains same. In composite section, you people know that the strain remains same. That means the strain in concrete is equal to, strain in concrete is equal to strain in steel. The strain in concrete is equal to strain in steel. We have to express the strain in terms of Young's modulus and as well as stress. We have to express the strain in terms of stress and Young's modulus. So strain in concrete is equal to FC divided by EC. Again Fs in terms of ES. FC by EC is equal to Fs by ES. FC by EC is equal to Fs by ES. We know that Young's modulus of steel are given as, now we are expressing Fs. In terms of EC. ES by EC into FC. See, we are expressing Fs in terms of FC. We are expressing Fs in terms of FC because we know the value of Young's modulus of steel and Young's modulus of concrete. Now substitute the value of Young's modulus and Young's modulus of steel and Young's modulus of concrete in this equation. So Fs is equal to, we know that EC has given us 2.0 into 10 to the power of 5 divided by 2.0 into 10 to the power of 5 divided by 0.14 into 10 to the power of 5. 0.4 into 10 to the power of 5. If you substitute the value of Young's modulus in this expression, we will get it as 2.0 into 10 to the power of 5 is the Young's modulus of steel, and 0.14 into 10 to the power of 5 it is the Young's modulus of concrete. We will get Fs is equal to 14.29. Fs is equal to 14.29 into Fc. Now we got Fs in terms of Fc. We got Fs is equal to 14.29 into Fc. And as usual, we know that, you know that the load shared by as usual we know that total load is equal to load shared by concrete plus load shared by concrete plus load shared by steel. We know that total load is equal this is the total load is nothing but it is the load coming on the column. Total load is nothing but it is the load coming on the column. So total load coming in the column is equal to load shared by the concrete as well as load shared by the steel. So total W is equal to PC plus PS. This is call it as expression number 1. So this is we can call it as expression number 1. So now we are expressing the expression in terms of load into, we are converting into expression in terms of stress and area. We are converting the term expression in terms of load into, we are converting expression in terms of stress and area, because we know the values of areas and stresses. We know the values of areas and stresses, so that we are converting expression in terms of load into expression in terms of stresses as well as Young's modulus. So total load W is equal to we know that stress FC is equal to PC divided by AC. I already told in the last problem. So Fs is equal to PS divided by AS. So we can get convert PC is equal to Fs into AS, equation number 2, and PS is equal to AS into Fs. This is equation number 3. See, in expression number 2 and 3 indicates we are expressing loads in terms of Young's modulus and stresses. We are expressing loads in terms of Young's modulus and areas, because we know the values of stresses and areas. So we are expressing loads in terms of stresses and areas. So PC is equal to AC into FC plus AS into Fs. So this is expression, we can call it as expression number 4. We can call it this expression as expression number 4. So substitute the values in expression in the equation number 4. We know total load is given, we know the total load is given as 360 kilonewton. So 360 into 10 to the power of 3. This is the total load given, that is the load coming on the column. 360 into 10 to So now we are converting the expression in terms of load into, in terms of stresses and areas, because we know the values of stresses and areas. So we are converting expression in terms of loads into areas into stresses. We have total load. We know that total load is equal to, total load is given as 360 kilonewton. 360 into 10 to the power of 3. We are converting from kilonewton to newton, because in all the stresses are given in newton per millimeter square. We know that area of concrete as, area of concrete as 87486.73. And another expression, we know that Fs is equal to 14.29 Fc. Fs is equal to 14.29 Fc. We have to substitute this equation in terms of Fs. So 14.29 into Fs as into 14.29 FC into, we know that area of steel as you know that area of steel as 2513.27 2513.27. This is the area of steel. So our intention here in this expression here only the unknown is FC. In this expression here only the unknown is FC. So if you solve this equation, we will get FC as, if you solve the equation, we will get FC as 360 into 10 to the power of 3, 360 into 10 to the power of 3 divided by 123376 123376.22. If we simplify this, we will get FC as 2.91 Newton per millimeter square. FC as 2.91 is FCS, that is the stress in concrete, will get as 2.91 Newton per millimeter square. In the same way, we know that the expression for concrete, expression for steel, that is expression for steel is Fs is equal to 14.29 FC. Fs is equal to 14.29 into FC. Fs is equal to 14.29 into FC. If you substitute the values of FC in this expression, we will get Fs is equal to 14.29, FC as a 2.91. We will get Fs is equal to we will get Fs is equal to Fs as 41.55 Newton per millimeter square. 41.5 Newton per millimeter square. This is the stress share. This is the stress in steel. 2.91 is the stress developed in concrete, and this is the stress developed in steel. In this problem, here one question extra is asked, that is here is to find out what is the load shared by each unit. That is the load shared by each unit. And here we can calculate what is the, here we can calculate, that is the load shared by concrete. Load shared by concrete. Load shared by concrete. Load shared by concrete. And this is, it's very simple to calculate load shared by the concrete, because we know the stress developed in concrete, and we know the area of concrete. Here we know the what is the stress developed in concrete as well as what is the area developed in concrete. We know that two values, that is stress developed in concrete and as well as area of concrete. So that it is very easy to calculate. So PC is equal to, we know that FC is equal to PC divided by AC. We know that FC is equal to PC divided by AC. So we need PC. PC is equal to AC into FC. So AC into FC, we know that the value of AC 274.86.73 into we know that stress is 2.91. If you multiply by, we will get what is the load shared by concrete. That is load shared by concrete, that is 254.58 kilonewton. This is the actually the load shared by the concrete. This is the actual load shared by the concrete. And another thing, so that here we have multiplied the area and stresses. If you multiply by the area by stresses, we will get what is the actually load shared by particular that material. So that after calculating the PC, we know that total load W is equal to, we know that total load is 360 kilonewton. We know that actually the load is Total load is 360 kilonewton. So we know that total load is equal to load shared by the concrete as well as load shared by the steel. We know that total load is equal to load shared by the concrete plus load shared by the steel. So W is equal to PS plus PC. So W is equal to PS plus PC. We need what is the actual load shared by the steel. So W minus PC. So 360 into 10 to the power of 3 minus load shared by concrete. So load shared by concrete is minus 254.58 into 10 to the power of 3. So we will get load shared by the concrete is 105.42. 105.42 is the load shared by the steel. 105.42 is the load shared by the steel. So that in this problem we are calculated what are the stresses shared by different materials and as well as load shared by the different materials. So we can take another problem, that is a problem on temperature, stresses and strains. So we can calculate another problem on temperature, stresses and steel. Here given as a problem as a steel bar 20 mm diameter and 6 meter long is subjected to two grips, one at each end at the temperature of 100 degrees centigrade. Determine the force exerted by the bar when the temperature falls to 20 degrees centigrade. If two conditions are given, grip do not yield and the grips yield by 1.2 mm. Data given on temperature stresses. Temperature stresses. So that the first condition we can take it as a, first we have to write down what is the given data. Given diameter of the bar D is equal to 20 mm. Given diameter D is equal to 20 mm. L is equal to 6 meter, that is 6000 millimeter. Third one T1 is 100 mm, 100 degree centigrade. T2 is 20 degree centigrade. 20 degree centigrade. Alpha is 12 into 10 to the power of minus 6 per degree centigrade. Alpha is equal to 12 into 10 to the power of minus 6 centigrade here given. So that another thing here given is Young's modulus C is equal to 2.1 into 10 to the power of 5 Newton per millimeter square. See, here there is a difference in temperature. Here the initial diameter of the bar is 20 mm. Here the initial diameter of the bar is 20 mm and length L is equal to 6000 mm. T1 is 100 degree centigrade and T2 is 20 degrees. See, this is a variation in temperature. That is very important. So that here our intention is to find out what is the actual stresses developed due to variation in temperature. So first case we can take it as grips do not yield. So that first condition, I already explained the theory about this. The first condition is grip do not yield. First condition, here two conditions are given. So the first one is grips do not yield. Grips do not yield. Here first condition is grips do not yield. So first, before starting of the problem, we have to calculate what is the first actually before starting the problem we have to calculate what is the area of steel. We have to calculate what is the area of steel. We have to calculate what is the area of steel. We know that area of a rod is equal to pi d square by 4. So pi is equal to 3.14 into given d as 20 mm. So 20 square divided by 4. Area of a steel as 314.16. 314.16 Newton per millimeter square. Area of steel is 314.6 Newton per millimeter square. So next question is next we have to find out Next, we have to find out what is the fall in temperature, because initially the temperature is 100 degrees Celsius, again it is a fall to 20 degrees Celsius. So T1 minus T2, this is actually the fall in temperature and we call it as a T. There is a difference in temperature variation. So T is equal to 100 minus 20 degrees Celsius. So we will get T as 80 degree Celsius. So this is a difference in temperature, T as 80 degree Celsius. So that now we have to find out what is the actually difference in temperature. So actually now we have to find out, actually we have calculated already what is the difference in temperature. Now due to this difference in temperature, we have to calculate what is the stresses developed in the rod. That's very important. Due to this variation in temperature, we have to calculate what is the stresses developed, what is the resistance developed in the particular rod. We have to calculate. We know that stresses, we know that stress is equal to, stress F1 is equal to, stress F1 is equal to alpha T into E, which I have already explained in the theory. Stresses is equal to alpha T into E. This alpha T is the strain. This alpha T is the strain into Young's modulus. That's all. This is the same basic concept. If you multiply by the strain into Young's modulus, we will get the stress. We the temperature, we have calculated already strain. Strain is alpha into T. This is the alpha is the coefficient of temperature. Alpha T is coefficient of temperature, T is the difference in temperature and E is the Young's modulus. So if you substitute these values, we will get actually what is the stress, this is temperature stress. So F1 is equal to alpha as 12 into 10 to the power of minus 6 into temperature 80 degree, temperature is 80 into 2 into 10 to the power of 5 into 2 into 10 to the power of 5. We will get F1 as, we will get F1 as 192. We will get F1 as 192. We will get F1 as 192 Newton per millimeter square. 192 Newton per millimeter square. Next, we have to calculate what is the actual force exerted. Now we have to calculate what is the actual force exerted in the bar. Due to what? We are calculating all the values due to the effect of temperature only. So because of the temperature effect, what is the force exerted by the bar? So because of the force effect, because of the temperature effect, what is the force exerted by the bar? So that there is a force exerted on the bar. Force exerted on the bar. Force exerted on the bar. Force exerted on the bar is stress into area. That is very simple. Stress into area. Stress into area. So we know stress is equal to 192, and we know the area of steel as 314 we know the area of steel as 314.16. 314.16. So we will get force exerted as 47752. 4772. 47752. 47752. 47752.32 Newton. 47752.32 Newton. This is the force exerted on the bar, and it is a condition in given: grips do not yield. That's very important. Grips do not yield. Okay. Here another condition is given: if the grips yield by 1.2 mm. If the grips yield by, the stress in the rod. Stress in the rod when the grips yield by, stress in the bar when the grips yield by 1.2 mm. Stress in the rod when the grips yield by 1.2 mm. This is very important. So expression for F2 is expression for F2 is alpha T, I already told in the theory, alpha T minus delta by T, delta by T, sorry, delta by L, delta by L, delta by L into E, into E. This is actually, this is the strain, that's all. This is the strain into Young's modulus, that is the same concept, strain into Young's modulus. Strain into Young's modulus. This is the change in length, that is the grip. What is 1.2 mm? This is the grip length, this is the virginal length. This is the grip and this is the virginal length. So F2 is equal to alpha is 12 into 10 to the power of minus 6 into falling temperature is 80, falling temperature is 80 minus 1.2 and length is given as 60 mm, 60 meters into Young's modulus, into Young's modulus ES, into Young's modulus ES 2.0 into 10 to the power of 5, 2.0 into 10 to the power of 5. We will get stress F2 as, we will get stress F2 as, 152 Newton per millimeter square. This is the stress developed when the grip yield by, this is the stress developed when the grip yield by 1.2 mm. This is the stress yield when the grip yield by 1.2 mm. So next step, we have to calculate what is actually the force exerted. What is actually the force exerted due to, what is the force exerted in the bar due to temperature effect, due to the temperature effect. So P is equal to stress into area. So what is the stress here? 152, area as 314.16, we will get forces 477, we will get 477 52.32 Newton. This is the force exerted by the bar. This is the force exerted by the bar due to the temperature effect. That is important. This is due to the temperature effect. That too in condition grips yield by 1.2 mm. So now almost all the problems in this chapter are same. We have to calculate the stresses and what is the force shared by in this material due to temperature effect. So today we have learnt today in this class we have learnt is how to analyze the composite sections, that too how much stress are developed in the stress are shared in this section, and what is the strains are developed in this section, and what is the load shared by this section, and also we have learned today what is the temperature effects we have studied and temperature stresses developed in this section we have studied. So that thank you for listening my video. It's a thank you one and all.